Welcome. Today I'm going to talk to you guys about efficiency. Efficiency is a helpful way to compare two different methods of doing work. Believe it or not, there's multiple ways to do work. You can use machines. Usually that's the most common way of doing work. Or you can do a brute force method where you just apply a force directly and get an object to move in a certain displacement. And so we can compare those methods by using something called efficiency. Efficiency is just a ratio of the two different types of methods that you might use. The machine method, or the whatever the modified method is that you use, and the brute force method. And so here I've drawn a couple of situations to illustrate this. So here's me, of course, you can see I'm super strong, lifting up a box to a certain height. And that height gives me how much distance it's moved or displacement it has. And so if I wanted to, I could multiply my force here by my displacement there and figure out how much work I did. Because remember, the work formula looks like this. Work equals the force, in this case the force is really large, times the displacement. And in this case the displacement is kind of small, right? I'm just moving it over a small distance. So I've written the displacement as kind of a small number, small letters, and then the force is a larger one. Now let's compare that with deciding, you can see I drew little pain lines by my knees. Let's say I have bad knees, which I kind of do. And it's hard to lift something that's really heavy like that. And so instead I employ a simple machine, like a ramp. And so I put the box on the bottom of a ramp and then slide it up to the top. Notice, in the end, I get it to the same height, so the end result is the same. But look at what I have to do to be able to do that. I apply a much smaller force as I slide it up the ramp over a much larger displacement. And so you can see that the work done here and the work done here are going to be different. In fact, if I were going to write it out, I could say the work here would be a much smaller force multiplied by a much larger displacement. So hopefully that makes sense. So you can see big force, small displacement, small force, big displacement. So here's what I drew. I drew out the characteristics for this. So if you're lifting it, you use less, you lift over less displacement or less distance. You apply more force, but there's no friction that you're fighting against. So all of the force that you use goes into moving the object over a certain displacement. And so as a result, because there's no friction, it has the least amount of work for any method to raise the box up to that certain height. On the other hand, if I come over here to situation 2, you can see that I had to apply it over more displacement, but I'm able to do it with less force. The problem, though, is I'm not just fighting against the parallel force that's down the ramp, I'm also fighting against friction. And that friction takes away some extra work. I have to do more work to push it up the ramp because of the fact that I'm doing work against the friction. And so as a result, it ends up being more work overall. This is what we call a trade-off. And you can see the trade-off here is you are trading displacement for force, right? So why don't you go climb a rope up from the first floor to the second floor to get to your science classes? Why do you have to take the stairs? Well, if you think about it, climbing a rope would be the least amount of work that you could do. The problem is that if you've ever tried to climb a rope, it requires a huge amount of force to be able to lift your body weight directly upward. It's much, much, much easier to lift your body weight slowly as you go up the stairs over a very much longer displacement. So instead of going straight up and down, now you're going at an angle. And as a result, you have to walk for a greater displacement, but you're able to use way less force. And because there's friction, it ends up being that you have to do more work as a result. Okay. So if we compare these two methods, so this would be the amount of work, let's say, that I'm doing with the ramp. Let's call that the amount of work that I put in. So I'm going to go ahead and change back here. So let's call that the work in. Why? because it's the work that I'm doing to use the ramp. What sort of work am I getting out of it, though? Aren't I just getting out of it the same amount of work that I would have had if I did the brute force method? Yeah. And since that's the least amount of work, I want to go ahead and compare how much more work I have to do to the least possible. And so this is my work out. The brute force method is always the work out. It's always as if you just lifted it straight up or moved it directly from one place to another. And as a result, we can take those formulas and plug them into this formula right here. The work out is the brute force method, right? So, oops. Brute force. In other words, you are just lifting it directly against the force of gravity, or you're taking the most direct method to do it. And so that's the work that you get out of it. We're going to see later on that it's also the work that gets stored in the object. So I'm going to go ahead and write that as well, because that's going to set us up for something called potential energy later on. The potential energy is the amount of work that gets stored in an object. The work that I had to put in is always going to be greater because of friction. And so that's the using some other method. So is it using a machine? Maybe. Is it using some other process? Could be. In the end, it's still getting the same thing done. It's just requiring that more work be done to be able to do that. And so this does not have to do with the energy. Some of this is wasted, and we'll talk about that in just a minute. Well, it does have to do with the energy, but it's not directly what's stored in the object. So this ratio right here is going to give you a number, and it's going to be a decimal number. So it's going to be from 0 to 1. If you had a perfectly efficient method, right, you'd have this number on the bottom and this number on the top would be exactly the same, and so your answer would be 1. If you had a process that required you to put in an infinite amount of work, you would have very close to 0. And so you can see that most methods are going to be somewhere in between. And we'll talk about some efficiencies in class. Efficiency is delineated or signified, I suppose is a better way to say it, with this Greek letter eta right there, which looks like an N with a curly tail in the front, which is weird, I know, but that's what it is. And again, you get a number that's between 0 and 1. Some people actually go to the next step and multiply it by 100% to give yourself a percent efficiency, but physicists will tend to just leave it as a decimal, and that's totally fine. Later on, you're going to see that the efficiency is also the amount of useful energy that you get out of a process compared to the amount of energy that you have to put into the process. And so as you see this particular diagram right here, this dashed line shows you what the system looks like. Okay, so this is your sort of graphic organizer of how energy works. So you put in a bunch of energy on this side, and then some process occurs. So we got a process right here. Something's going on inside the system. I don't know what it is, but as a result, usually through friction bleeds off some of the energy into this goes outside of the system as non-useful thermal energy or heat, right? So it heats up the.
Mr. Kozlowski,
sorry.
Please dial 4518.
So it heats up the system, and then that heat bleeds off into the environment around the system, unfortunately. So that the system heats up the environment a little bit, and as a result, some of the energy gets bled off. And so that's what ends up happening here, right? So as you're sliding this up the ramp, the friction is causing the box and the ramp both to heat up, and that heat bleeds off into the atmosphere. That thermal energy bleeds off into the atmosphere, and we can't use it to do anything. And so as a result, we end up with less here than we had at the beginning. And the difference between how much we have here and how much we have here is the efficiency. So hopefully that makes sense. Any friction or any other resistive force is going to drain useful work and energy from the system. So anytime air resistance, anytime you've got anything like that, it's going to bleed off work from the system. Hopefully that makes sense. We're going to start transitioning into using machines, and so make sure that you've got this down, because we're going to be using this efficiency to be able to compare different methods in the coming days. Thanks.